Hello everyone. In this video, I am going to go over section 5.3 equations of equilibrium, also section 5.4 2 and 3 force members. A body is subject to a system of forces that lie in the xy plane. When this is in equilibrium, we not only need my sigma F equal to zero, so net force equal to zero, also will also need net moment equal to zero. So other words, this thing has no, when we say something rigid body has is in, when we say rigid body is in equilibrium, it means that there's no translational motion, there's no rotational motion as well. So we have our three equations: sigma fx equal to zero, sigma fy equal to zero, sigma moment equal to zero, where point O is any arbitrary point in the rigid body. And please know that these equations are the ones most commonly used for solving 2D equilibrium problems. There will be two other sets of equilibrium equations that we don't use it as often. Please refer to the textbook for further details. The solution to some equilibrium problems can be simplified if we recognize members that are subjected to forces at only 2 points. For example, we have point A, point B in the figure below. If we apply equations of equilibrium to such a member, we can quickly determine that the resultant forces at A and B must be equal in magnitude and act in the opposite direction along the line joining point A and B. Here's a real life example. Member AB can be considered as two force members provided that their weight is neglected. This fact simplifies the equilibrium analysis of some rigid bodies since the direction of the resultant forces at A and B are known along, and it's also along the line joining point A and B. General steps. We're gonna first determine the XY coordinate. Majority of the time, X will be horizontal, Y will be vertical, but sometimes we're going to need to rotate the axis a little. Second step will be draw the free body diagram. And then lastly, we're going to apply three equations of equilibriums to solve for our unknowns. If there are more unknowns than the equations, then we call it indeterminate situation. We cannot solve these problems just using statics if we have more unknowns than equations. And then the order in which you apply equations, it may affect the simplicity of the solution. If we have two unknown vertical forces and one unknown horizontal, then we do the horizontal equation first. Whichever equation is simpler, we do that equation first. And then number three, if the answer for an unknown comes out as negative number, that does not mean it's incorrect. Negative number, it just means that the sense or direction of the unknown force is the opposite to that what we originally assumed. I will show you some examples in a little bit. This one right here, we know that point A and point B are both pin support, meaning the reaction force coming out from A and B will be both horizontal AX and AY, DX and DY, horizontal and vertical. But for this one, since we're only looking for the support reaction at point A and point C, that means we're going to looking at only the member AB. Here's our free body diagram for the member AB. For your A, you have your AX and AY, external force B coming down, and also you have a support from FCD. We're going to write our moment equation. Point summation of moment about point O says that 4 kilonewton is generating a moment. 4 kilonewton is generating a moment. This is clockwise. And then the moment arm is 1.5 meter plus another 1.5 meter, 3 meters total. So that's where that term comes from. And then the next thing is that you have that FCD. We can break that FCD into the horizontal component and the vertical component. Only the vertical component of that FCD is generating moment because horizontal component of that FCD go through the axis of rotation. When we say axis of rotation, in this case, is point A. Okay, horizontal component of the FCD go through the axis of rotation. Therefore, it's not in there. Okay, so it's only the vertical component, which is FCD sine 45 times the moment arm, which will be 1.5. Then next, we're going to write our, excuse me, sigma fx equal to 0. So sum of all the forces horizontally equal to 0. So you have your ax, and you have your horizontal component of your FCD, and then also you have your sigma ay equal to sigma y equal to 0. All the forces on the vertical direction in our case will be ay, and then the vertical component of your FCD plus the negative 4 kilonewton because it's going down. Okay, so there's our three equations and three unknowns. We're solving for ax, ay, and FCD. Notice that FCD comes out positive. AX and AY both come out to be negative. Negative means that the actual direction of AX and the actual direction of AY is the opposite of what we originally assumed in the free body diagram. So in the free body diagram, your AX go to the right. That means the actual direction of your AX is going to the left. Same thing similarly for your AY. The the free body diagram says AY goes up, and we calculate our result come out to be negative 4 kilonewton for AY. That means the actual direction of your AY is coming down. Next example over here, we have roller support at point A. Okay, that means you have reaction force at point A only is there's one perpendicular to the surface. Pin support at point B, that means reaction force at B, you have your Bx and your By. And also we have a distributor load. In the previous chapter, we talk about if it's a distributor load, that we can replace that with equivalent one single point load. And the magnitude of that single point load will be the area of the rectangle, which will be 3 kilonewton per meter times 4 meters. The area of the rectangle will be 12 kilonewton. Okay, and the location will be the centroid of this rectangle, which so overall the width of the rectangle is 4 meters. That means the equivalent pointing load will be 2 meters away from the point B. There it is, 12 kilonewton, 2 meters away from point B. And then NA, and then your BX and your BY. There's my free body diagram. Next thing, we're going to write an equation moment about point B. And PowerPoint here asking, why do you do point B? The reason that you pick point B is that you want to pick a point to write the moment equation. And this point to write your moment equation needs to be the point that you have most unknowns. In our case, point B has the most unknown. You have BX and BY. Why do we pick the point that has the most unknown? Because when picking this point, right, we have a lot of unknowns, and all this unknowns is going to go through the axis of rotation. So in other words, if we pick point B as the axis of rotation moment about point B, BX, both the BX, BY, two unknowns here, they have zero moment arm because they go through the axis of rotation. This will simplify our calculation, simplify our moment calculation. You have lots of zeros. So that's why in sigma and B, moment about point B, BX and BY are not even in there because BX and BY does not generate any moment about point B. If we do the moment about point A, then yes, BX and BY both are generating moment. So we're picking point B because these two are unknown. The moment are zero. So that way, this will simplify our calculation. Only NA in this case is generating moment. It looks like we're breaking down our uh, NA into the horizontal component and the vertical component. Both the horizontal component and the vertical component are generating moment. So let's take a look. Your NA is here. Vertical component is that. Okay. Pardon my sketch here. Horizontal component is that. Horizontal component, look, your moment arm is this much, and it's also the same as this much. So that means the horizontal component, the moment arm, is going to be 3 meter times sine 30. Okay, so that's where that comes from. Okay, and then also the vertical component is generating moment as well. Okay, vertical component, your moment arm is going to be this portion. So it's 4 meter plus 3 meter cosine 30. Okay, that's where that comes from. There's your 4 meter, it's this portion, and then also this portion that is going to be 3 cosine 30. Add that together. Both of them are trying to generate about point B clockwise. That's why both of them are negative. Okay, this one is trying to go this way, hey, clockwise. And then the horizontal one is trying to go this way, hey, clockwise as well. Okay. And then lastly, you have 12 kilonewton. 12 kilonewton is going this way. 12 kilonewton is going this way counterclockwise. That's going to be positive. So it will be 12 kilonewton times 2 meters as well. So one equation, then in this equation, we only have one unknown, which is Na. We're solving for the value of Na. Next, we're going to do our equation sigma fx equal to 0, sigma fy equal to 0. So again, we wrote our Na into horizontal and vertical, and there's that bx and by. So overall, we're going to write our equation in ax bx, all the x go together. Okay, there's your nx and bx, it's going to the left, that's negative. And also you have your nay, which is this one, and your y component, you also have the 12 kilonewton coming down and by going up. That's why, that's the y equation. So we're solving for bx and your by in both these two equations. So overall, 3 equations and 3 unknowns. This is all I want to show you in this PowerPoint that covers the section 5.3 and 5.4. Thank you for watching.